Polyethylene is a thermoplastic polymer derived from the polymerization of ethylene monomer. It is considered as an addition polymer. There are three types of polyethylene, which is low density, high density, and linear low density.
So let's move to the next one, which is the significance of polyethylene. First, packaging industry. The application of packaging industry is plastic bag, shrink wrap, and bottles. The benefit of the packaging industry, it is a lightweight, moisture resistant, and cost effectiveness make it ideal for packaging. Second, construction industry. It has been used as a pipes, insulation materials, and geomembranes. And the benefit of construction industry is it has a HDPE, which is particularly valued for its strength and chemical resistance. Number three, automotive industry. Application, full tanks, dashboard, and protective covers. And the benefit of automotive industry is offer durability and weight reductions and improving fuel efficiency. Number four, healthcare sectors. The application of the healthcare sector is prosthetics, medical tubing, and pharmaceutical packagings. And the benefit is it is non-toxic, sterilizable, and ensuring safety for medical use. And the last one is electrical and electronic industry. The application for this industry is cable insertions and protective covers. The benefit is high dielectric strength and resistant to environmental factors.
Bulk polymerization. Bulk polymerization is a method used to produce polyethylene PE by polymerizing ethylene monomers in their purest form without the use of solvent or dilutes. The reaction occurs in a high pressure or low pressure environment depending on the process used, such as free radical, synchronata, or metallation catalyst. The polymerization can be initiated thermally, catalytically, or through radical mechanisms. There are 5 fundamental principles of bulk polymerization for PE. First, purity of monomer. Ethylene gas is compressed and purified to remove impurities, ensuring a clean reaction environment. Besides, initiation. The reaction is initiated by catalyst or high pressure or temperature for free radical polymerization. Other than that, propagation. Ethylene molecules react to form long-chain polyethylene polymer. Furthermore, reactor types. The reaction typically occurs in a stirred autoclave reactor or tubular reactor for free radical processes or in a loop reactor for catalytic process. Finally, heat control. Heat generated during the exothermic polymerization reaction is managed using advanced cooling systems.
Advantage of bulk polymerization for PE. First one is high purity of polymer, as no solvent or diluents are used. The resulting PE is free from contamination. The second one is simple recovery. The absence of solvent simplifies polymer recovery and reduces the need for extensive separation step. The last one is high reaction rates. In catalytic process, high reaction rates can be achieved due to the high concentration of ethylene monomers. There are 2 disadvantages of bulk polymerization for PE. The first one is heat management challenge. The high exothermicity of the polymerization reaction can make heat dissipation difficult, leading to potential hotspot. The second one is viscosity increase. As the polymer forms, the viscosity of the reaction mixture increase, making mixing and heat transfer more challenging. Example of product and application. Polyethylene produced via bulk polymerization is widely used in application that require high purity and tolerant material properties. For the first one is high density polyethylene HDPE for the application of bottles, containers, pipes, and automated food tanks. For second one, low density polyethylene LLDPE for the application of stretch film, packaging films, and agricultural films.
Move to key principles. First, we have solvent role. The solvent acts as a heat sink, helping to dissipate the heat generated during polymerization. Additionally, the solvent's viscosity, polarity, and thermal conductivity directly influence the reaction kinetics, molecular weight and distribution, and branching of the resulting polyethylene. These properties ensure consistent polymer quality and enable fine-tuning for specific applications. Second, we have catalysts. Similar catalysts such as Ziegler-Natta or metallosinase are used as in bulk polymerization. Next, we have reaction conditions. Moderate to high temperatures, which is 150 to 300 degrees Celsius, and pressures are applied.
Emulsion polymerization. Emulsion polymerization is the process of emulsifying a monomer with a surfactant in an aqueous solution to generate droplets that then polymerize to produce controlled size polymer particles, usually between 50 and 500 nanometers. Key steps in emulsion polymerization. First, preparation of the emulsion. The monomer such as ethylene or styrene is emulsified in water with the help of surfactants, which lower the surface tension between the water and the monomer, allowing the monomer to form tiny droplets in the aqueous phase. Initiator. A water-soluble initiator is added to the emulsion. This initiator decomposes to form free radicals, which start the polymerization reaction by attacking the monomer droplets. Propagation. The free radicals add monomer units to the growing polymer chain. This process occurs within the micelles where the monomer concentration is higher. Fourth, termination. The fifth, coagulation and recovery. Application in polyethylene production. First, monomer. Second, initiator. Third, polymerization. Fourth, polymer recovery. Essential principles. First, monomer emulsification. Second, polymerization mechanism. Third, micelle formation. Fourth, formation of polymer particles. Key factors influencing emulsion polymerization. First, surfactant concentration. Second, monomer and initiator concentration. Third, temperature. Fourth, particle nucleation. Five, chain transfer and termination. Six, water to monomer ratio. Seven, stabilizers and additives. Eight, pressure. Advantages. First, high polymerization rates. Second, control over molecular weight. Third, lower energy consumption. Fourth, good particle control. Fifth, water-based process. Disadvantages. First, monomer solubility limitations. Complex process control. Third, limited for high density PE. Fourth, emulsifier residue.
Example of products and application. First, packaging films. The product is packaging applications. Second, coatings and adhesives. Third, agricultural films. Next, molding compound. Other than that, surface modifiers. Next, extrusion coating. 7, foam products. Pressure sensitive adhesive. 9, water-based emulsions. Lastly, consumer goods.
Suspension polymerization, also known as a bed or pill polymerization. It involves dispersing the monomer ethylene into a continuous liquid medium, commonly water, with the help of stabilizer or surface pen. The process used as an initiator soluble in the monomer phase to trigger polymerization. The monomer droplets act as isolated microreactor, resulting in discrete polymer bits or particles. In polyethylene production, suspension polymerization is less common compared to the gas phase or solution method. Fundamental aspect of suspension polymerization.
The fundamental aspect of suspension polymerization divide by 6, which is monomer dispersion, initiator, stabilizer, polymerization reactions, control of particle size, and post-processing.
Advantages of suspension polymerization for PE. Uniform particle morphology. Its produce well-defined spherical particle ideal for further processing. Instant heat management. The water medium absorbs the heat generated during polymerization. Scalability. Suitable for large-scale production with consistent quality. Disadvantages of suspension polymerization for PE. High water usage. Required a significant amount of water, leading to environmental and disposal concerns. Second, complex separation. The need to filter and dry the polymer bits increase operational complexity. Limited monomer compatibility. More suitable for certain types of monomer. Ethylene high pressure requirement can complicate the process. Products and application utilizing suspension polymerization for PE. First, high-density polyethylene (HDPE) beds used in application like injection molding and rational molding where uniform particle size is crucial. Specialty polyethylene grades tailored for application requiring precise particle characteristics such as in sintered or powder form. And composite materials. Polyethylene beds produced via suspension polymerization are often used as a fillers in composite or as a precursors for advanced materials. gas-phase polymerization for polyethylene production. Gas-phase polymerization is one of the most widely used method for the industrial production of polyethylene (PE), particularly high-density polyethylene, which is HDPE, and linear low-density polyethylene (LLDPE). This method involves the polymerization of ethylene gas in the absence of a liquid medium, using advanced reactor design and catalytic systems to produce high-quality polymer granules efficiently.
Next, we will discuss about core principles of gas phase. First, monomer and catalyst in the gas phase. Second, polymerization process. Third, polymerization reaction. Fourth, control of molecular weight and structure. Fifth, polymer formation. Key conditions in gas phase polymerization. First, temperature from 60 to 300 degrees Celsius. Second, pressure in the range of 20 to 40 atmospheres. Third, monomer concentration to maintain a high rate of polymerization. Fourth, catalyst type and activity. For example, zinc-nata catalyst, metallocene catalyst, or chromium-based catalyst. Fifth, fluidized bed reactor. Sixth, residence time. Lastly, temperature control and heat removal.
Products and application. Polyethylene produced via gas phase polymerization is used in various applications that require specific mechanical and physical properties. The first one is high density polyethylene HDPE. The application are bottles, household containers, pipes, and fuel tanks. The characteristics are high strength, rigidity, and resistance to chemicals. For the second one is linear low density polyethylene LLDPE. The application are stretch wrap, films for food packaging, garbage bags, and agricultural covers. The characteristics are excellent flexibility, puncture resistance, and tensile strength. The third one is polyethylene for injection molding. For the application are toys, caps, closures, and household goods. The characteristics are high impact strength and processability.
Let's move to the comparison for the fast polymerization method. From the aspect medium, bulk used as a pure monomer solution use a solvent. Emulsion use the medium of water, while for the gas-phase polymerization use gas. For heat dissipation, it is challenging for bulk and efficient for solutions, excellent for emulsion, good for suspension, and moderate for gas-phase polymerizations. The water used for solution, emulsion, and suspension are very high compared to bulk and gas-phase that doesn't use any water. Next, for aspect polymer recovery, it is complex for solution and emulsion, moderate for bulk, and simple for suspensions and gas phase. Other than that, product application for bulk and gas phase are HDPE and LLDPE. For solution, it is for HDPE, LLDPE, and UHMWPE. For emulsion, product application is rarely used due to difficulties in producing high molecular weight. And for suspensions, it is used as a specific form polyethylene. Lastly, energy efficiency for bulk and solution are moderate. For emulsion and suspensions are high, and for gas phase, energy efficiency very high.
Strength and weakness. First, gas phase polymerization. The strength is high production efficiency, good control of polymer properties, energy efficient, minimal solvent use. For the weakness, limited to HDPE, LLDPE, catalyst sensitivity, heat management challenges. Second, slurry polymerization. For the strength is versatility, high purity, efficient heat removal, high yield. For the weakness, solvent usage and recovery, complex process control, not ideal for all PE grades. Lastly, solution polymerization. For the strength, control polymerization, suitable for LLDPE and HDPE, good heat management. For the weakness, solvent recovery issues, limited scalability, environmental concern due to solvent use.
Comparative analysis for bulk polymerization. For monomer phase, it's monomer only. The polymer type is HDPE. The key advantages are simple, cost-effective, and high purity. The key challenge are heat management and exothermic nature. For the strength, high polymer purity, simple process, efficient recovery, high polymerization rates. For the weakness, heat management issues, increased viscosity, and catalyst sensitivity. The key application are HDPE for rigid packaging, pipe, automotive parts. The suitable industry are packaging, construction, and automotive. From here, by understanding polymerization methods in the polyethylene industry, we can understanding the strengths and weaknesses of each method enables the selection of the most suitable process for producing polymers in desired properties. Besides, tailoring methods and leveraging specific catalysts allow the creation of polyethylene with unique features such as high durability, flexibility, and recyclability. Finally, choosing energy efficient and low pollution processes reduce production costs and promotes environmental sustainability.
In conclusion, understanding polymerization methods in the polyethylene industry is vital for optimizing production and customizing material properties. Different techniques like free radical, Ziegler-Natta, and metallocene catalysts offer unique benefits that meet the growing demand for high-performance, cost-effective polyethylene. This knowledge drives innovation and supports sustainable material development across various industries.